You may recall we mentioned at the beginning of the lesson that there were two ways of assessing the descent performance. We have covered the angle of descent, or descent range. Now let us consider the rate of descent, or descent endurance. You have already learnt in an earlier lesson that the rate of climb was a function of both climb angle and velocity. Similarly, the rate of descent is a function of descent angle and velocity. Shown here is the angle or gradient of descent formula that you have already learnt. All that is needed is to add the velocity function as shown. This is now the formula for the rate of descent. You may recall that force and velocity gave us power. So the correct formula for the rate of descent is the one shown. The rate of descent is equal to the power required minus the power available divided by the weight. Power required minus power available gives excess power required. So for any given weight, the rate of descent is determined by the excess power required. The greater the excess power required, the larger the achievable rate of descent. Conversely, the lesser the excess power required, the smaller will be the rate of descent. In an emergency descent, for instance a descent initiated by the pilot following depressurization, the aim is to reach flight level 100 as soon as possible. The regulations state that flight level 100 must be reached within 10 minutes. To achieve this requirement, the aeroplane would need to lose height with the maximum possible rate of descent, which can only happen if the aeroplane has maximum excess power required. Shown here are the power required and power available curves for both the jet and propeller aeroplane. The areas beneath the power required curves but above the power available curves represent the excess power required and are highlighted in light blue. In order to create the conditions of the greatest excess of power required, power available must be reduced to nil, as shown here. Notice that the blue areas of excess power required are now as large as possible. In order to achieve the greatest rate of descent, the aeroplane needs to fly at a speed that achieves the greatest excess power required. It is obvious from the graph that this can only be achieved at very high speeds. Remember that power required is a function of speed and drag. Therefore, the aeroplane needs to be configured for high drag and high speed in order to achieve maximum power required. In fact, for a lot of Class A aeroplanes, emergency descents are flown at maximum operating speeds with air brakes or speed brakes deployed and thrust at idle. If it were the aim to descend at the lowest rate of descent, the aeroplane would need to fly at a speed that gives the minimum excess power required. On the graphs, this point is plain to see. In fact, it is found at the very bottom of the power required curve. You may recall that this speed is called VMP. So to lose height at the slowest possible rate of descent, the aeroplane would need to fly at VMP. The lowest rate of descent is also known as maximum descent endurance, which essentially means the aeroplane will take the greatest time to descend. Let us now examine what factors will affect and modify the angle and rate of descent. The first of these factors is weight. For the moment, let us assume a normal descent at zero thrust whilst maintaining a standard scheduled descent speed. Looking at the diagram, a heavier aeroplane will have a greater weight apparent thrust. This creates more forward force than rearward force, and the aeroplane would accelerate. Therefore, in order to maintain the same speed and to provide extra lift to balance the weight, the aeroplane's nose must be raised. This increases the angle of attack and therefore the lift, but it also keeps the forward force of weight apparent thrust the same as the excess drag. Therefore, a constant speed is maintained but at a shallower angle. So under normal conditions, at a constant speed, an increase in weight decreases the angle of descent and therefore decreases the rate of descent. However, descent profiles are complicated as some aeroplanes, namely Class A aeroplanes, change their speed characteristics constantly during the descent profile. However, let us now consider the effect of weight on the minimum angle of descent or shallowest glide angle. You may recall that in order to achieve the minimum angle of descent, the aeroplane needs to fly at VMD, which gives the best lift-drag ratio and an angle of attack for 4 degrees. If mass is increased, VMD is increased. Therefore, our heavier aeroplane needs to fly faster to attain VMD. This concept will be shown through this next sequence. A heavier aeroplane will have a greater magnitude of weight apparent thrust. If left unchecked, the aeroplane will accelerate to a higher speed. As the speed increases, lift force will increase, but so will the drag force. Eventually, there will be enough total reaction to balance weight and enough drag to balance weight apparent thrust. At this point, the forces are balanced and a new higher steady speed is attained. This new higher speed is still VMD and the angle of attack is still 4 degrees. As you can see, the angle of descent has remained constant throughout. You may recall that increases in weight cause both the drag and power required curves to move up and to the right. Remember that this has the effect of increasing the speeds. Therefore, with higher weights, VMD, the speed for minimum angle of descent, and VMP, the speed for minimum rate of descent, will both increase. In summary, therefore, weight has no effect on the minimum angle of descent, but it will increase the speed along that descent gradient, and therefore it will increase the rate of descent. The next factor to affect the angle and rate of descent is the aeroplane's configuration. Looking at the diagram on screen, if the flaps or undercarriage were deployed, then excess drag would increase. To balance this increase in excess drag, the nose must be lowered. This action increases weight apparent thrust and a balance of forces is restored, but more importantly, the balance is achieved at a higher angle of descent and therefore a higher rate of descent. The effect of configuration can also be seen using graphs. Shown here are the drag curves for the jet and propeller aeroplane with excess drag shown by the light blue area. With flaps and undercarriage deployed, you will recall that the curves move up and left. This has the effect of increasing the excess drag and therefore increasing the angle of descent for any given speed. Notice too that the speed for the minimum angle of descent, VMD, is lower. The same effect can be seen when examining the rate of descent and by using the power required graphs. Similarly, the light blue area represents excess power required. With flaps and undercarriage deployed, you will recall that the power curves move up and left. This has the effect of increasing the excess power required and therefore increasing the rate of descent. Notice too that the speed for the minimum rate of descent, VMP, is lower. In summary then, with gear and flaps deployed, the angle and rate of descent increase, but the speeds for minimum angle and minimum rate of descent decrease. The last factor to affect the angle and rate of descent is wind. The diagram shows a descent angle and descent range with no wind. If there is a headwind blowing, the aircraft will move backwards relative to the no-wind diagram. This steepens the glide angle and decreases the descent range. However, notice that the aeroplane reaches the same descent altitude in the same time as the aeroplane flying in zero-wind conditions. This demonstrates that a headwind, which steepens the angle of descent, has no effect on the rate of descent. Conversely, if there was a tailwind blowing, the aircraft will move forwards relative to the no-wind diagram. This flattens the glide angle and increases the descent range. However, notice that the aeroplane reaches the same descent altitude in the same time as the aeroplane flying in zero-wind conditions. This demonstrates that a tailwind which flattens the angle of descent has no effect on the rate of descent. The effect of the wind on the angle of descent can be examined a little further. Because of the adverse effect of the headwind on the angle of descent, then in a glide, it would be of a benefit to increase the aeroplane's forward speed slightly. This has the effect of reducing the time spent in the headwind. This means that the aeroplane will not be pushed back as much by the wind. Similarly, with a tailwind, because a tailwind benefits the glide by decreasing the glide angle, it would be better to try and stay in this situation for longer. So this time the aeroplane's forward speed can be decreased so that the aeroplane can stay under the tailwind effect for longer and therefore be pushed further forwards. When flying on a training sortie, make sure you know the wind speed and direction, both for the surface and aloft. This will help you plan a better descent, giving you more accurate circuit patterns. But more importantly, knowledge of what the wind is doing will ensure you obtain maximum descent performance if an engine failure should occur. This completes the lesson on the general principles of descent. In this lesson you should have learnt the difference between angle of descent and rate of descent and the factors that determine them. Whilst most descents will start at a scheduled predetermined point called top of descent, and they will be uneventful, there will certainly be occasions when a pilot is rerouted and, in the worst case, suffer an engine failure. Under these circumstances, your knowledge of descent performance will be vital to ensure you carry out the correct actions and clear obstacles during the descent. More detail on the descent performance of different aeroplanes and the regulations that apply to these aeroplanes in the descent will be covered later.